Just a short overview of what's going to be covered in this particular video. The reason why the myESP32DB controller was built in the first place is because there is another project called mySQM Plus, which supports a whole range of sensors and other devices and stuff, like a weather station if you like. And as everybody sort of got into that project, it became apparent that when we started adding new and new sensors and all sorts of other devices, it got to the stage where it actually outgrew the PCB, and we would have to go in and generate a new printed circuit board and schematic for each edition. And about halfway through that process, it became pretty obvious that that was a losing strategy. So what we decided to do was create a new board, and this new board was called myESP32DB. And this board would be a daughter board, which one could talk to other daughter boards out there, other IoT devices, and they be able to upstream that into the mySQM Plus controller, and therefore have access to all this other data sitting around, or this other sensor data that's sitting around. And about halfway through this project, we realised that there were people who might want to use this and not use the mySQM Plus controller, but have this as the main controller talking to other IoT devices. And so we added upstream capability to things like MQTT to allow that to happen, and also introduce the role of the access point, because previously this just used to be a station. So the board itself is quite miniature, it's cheap, it's inexpensive to build, and it has a whole lot of extra features thrown in terms of how we can manage the various sensors and the various data and what to do with that, as well as be able to update the firmware and data files using over-the-air updating. Right, and so the next part is about looking closely at how this board is actually laid out. Now, the Gerber files are free, and you can just download the Gerber file from the link, and then you upload it to something like JCL PCB to be able to generate the actual boards and order them online. We have nothing to do with that. So the design was, let's be able to use relays so we can turn things on and off. Let's have some pins available so we can use digital input-output pins. They can be input, which reads the state, or they can be output, which controls some other state, as well as support for I2C sensor devices. This is the schematic for the myESP32DB. We've got a reverse protection diode, of course. We've got a polymer resettable fuse, the trusty 7505 regulator. Here are the relays, which are connected to D32 and D33. So it supports two relays, and here are the outputs to the relays. We've got positive and negative, as well as a signal where we can turn the relay on and off. And these are powered by a 2N7000 MOSFET, because the logic level coming out of the ESP32 chips is 3.3 volts, and that would be insufficient to drive the relay. So we use the 2N7000 to up that voltage to 5 volts, so the relay will actually switch on and off. We got a J13, which provides 5 volts to anything that you want. We've got a J11 connector, which provides ground outputs. We've got J12, which provides 3.3 volts out. So you can connect up devices like that. Coming over to I2C, we've got 3 connectors for I2C. We've got J5, J6 and J16. And for the digital I/O pins, we've got J9, J10 and J14. And those pins can be figured as inputs or outputs. So that's basically the board. We've got noise suppression on the various I2C and pull-up resistors as required. In terms of pin designations, this is the myESP32DB controller chip, and the PC board is made for this 30 odd pin controller called a dev module, and other ESP32 chips around, or modules around, sometimes won't fit because they're too wide or they've got too many pins. So you need to make sure that you get the dev module correct in order to get this and make it be able to fit the PCB. So this diagram shows you where the relays are connected, where the I/O pins are connected, and where the I2C bus is connected, as well as where we provide 5 volts and 3.3 volts and ground. Right, this is the actual layout of the PCB. It's quite small, it's 83 by 54, which is quite compact, and everything's silk screened. So on the top of the board you've got a number of, you've got each of the connection points defined, so you know where things are and be able to plug them in. R4 is 330 ohms, 330 ohms, and so on. And all of these resistors here, of course, would be quarter watt resistors. So those are all the connections. The big chip, ESP chip, fits here, and you have to make sure that the VM pin goes to the bottom left here, looking at the particular board. Here's the 3.3 volts output. Here's the ground outputs, and we've got other particular outputs for relays, etc. This is where you put the fuse. This is where you put a 12 volt lead to show that power is running. The I2C connectors are up the top here. Noise suppression capacitors are sitting here, and so on. Right, next up, the wiring diagrams. So to show you how to connect everything together, we've provided a whole lot of wiring diagrams for you, which shows you how the various things are connected. So for example, the relay here goes VCC, ground, and in. So in goes to signal, ground goes to ground, and 5 volts red goes to the VCC pin. NO and COM, normally open and common, or normally closed and common. We use normally open, so any device would be connected between COM and NO, because that's normally open. That's what NO stands for, normally open. And when we activate the relay turns on and closes the connection between NO and COM, and that triggers whatever device is out there. If we didn't do it that way and we used NC, what you'd find is the moment you turn the device on, these outputs would be actually connected together and would trigger the device, trigger whatever device it was connected to, and that's a bad thing. So that's why NO is used. Just to show you how you would connect, for example, switches as input devices, and how you would connect LEDs with output devices. This particular case, this LED doesn't have a built-in resistor. It's just a standard LED, so you can't really provide 5 volts direct to it. You have to use a limiting current resistor to ensure that it doesn't draw more than 20 milliamps. And here's an example of connecting a BME 280 device. It's an I2C sensor to J5, the I2C connector, 3 volts to V in, ground to ground, SCL to SCL, and SDA to SDA. These sensors, even though they're rated at 5 volts, will run quite happily with 3.3.